Hello, I'm Andrew, and this is my Magnet Breaking with Faraday's Law lab for Physics 2212. For this lab, I dropped a magnet through an aluminum pipe and analyzed the interaction of these objects. In this experiment in particular is to show that the magnetic force from the aluminum pipe slows down the gravitational force acting on the magnet. The purpose of this lab is to collect data such as the magnetic field, force, and current from the described interaction, and to create a computational model and compare the time it takes for the magnet to fall through the pipe in the real and computational experiment. The main result of this lab is that the experimental time was 1.252 seconds, while the computational was less than that at 0.822 seconds. Some of the concepts and formulas I used in this lab were Ohm's law, which is voltage equals current times resistance, the Biot-Savart law, shown here, the formula for magnetic flux, and Faraday's law, which is EMF equals negative change in magnetic flux over time, and Newton's second and third laws. Some of the initial conditions here is that the length of the aluminum foil was 0.3 meters, its width was 0.006 meters, inner radius 0.026 meters, radius 0.031 meters, and the mass was 0.025 kilograms. The system was a bar magnet in the aluminum tube, and the surroundings were everything else. Some assumptions that I made was that air resistance is negligible, the magnetic force and gravitational forces are the only forces acting on the system, and the bar magnet acts as a magnetic dipole. So here's the procedure and some of the data I collected. I did the experiment by dropping the bar magnet down the aluminum foil, which acted as a tube, and then I timed how long it took for the magnet to reach the bottom. I did this for 5 trials. I found that the average time was 1.252 seconds. So moving on to the computational model, here is some of my code. First, I inputted the constants, and then inputted some of the measurements of the aluminum foil, like its length, width, and inner radius, and then the magnet values, like its mass and its dipole moment. And then I created a function for the magnetic field, shown here, which utilizes the Biot-Savart formula, and then created another function for the magnetic flux. This code here both calculates the magnetic force from the tube onto the magnet, but also the magnet onto the tube, which is summed here into the magnitude of the magnetic force. And here shows the code for the gravitational force, and then the net force is adding the gravitational force and the magnetic force. And then we use Newton's laws to determine the velocity and position. And then this code results in the velocity time graph shown here. And we can see that at the start that it has a steep slope downwards, which means that's gaining velocity, meaning that there's a non-zero force acting on it. And this is because the force of gravity is stronger than the magnetic force at the start. But then we can see in the middle, the bar magnet stops accelerating and remains at a constant velocity. And this is because the gravitational force and the magnetic force are equal. But then it continues to accelerate again here. And this is because the gravitational force becomes greater than the magnetic force. And then this depiction here shows the 2 poles of the bar magnet, the blue end being south pole, or the negative end, and the red end being the north pole, or the positive end. And we can see here that the time in the tube in the computational model was 0.822 seconds, which was less than the experimental average time. In the simulation, the color of the tube indicated the direction in which current was flowing. We know that the red is flowing in the counterclockwise direction, while the blue is flowing in clockwise direction. And we can use Lenz's law to determine this. If you were to flip the magnet around in this experiment, it would fall in about the same amount of time, but the direction of the current would flip. Comparing the real-time experiment versus the computational system, the times were similar, but the computational was a bit shorter. Adding more rings and accounting for air resistance in the simulation would have made it more accurate. The shape of the velocity time graph shows that the gravitational force is greater than the magnetic force while entering and exiting the tube, but is equal to it while inside the tube, which was mostly explained in the last slide as well. There are some sources of error in this experiment, one of which was any error that I had in timing the real-time experiment. And the other source of error was air resistance, which the computational model did not account for and may have made the difference between the real time and the computational model time. If the resistivity of the conductor were reduced as possible to zero, it would have increased the current according to Ohm's law, which states that current equals voltage over resistance. And then an increased current would have caused the magnet to fall even slower. If holes or slots were cut into the tube, this would have caused there to be less rings, which would decrease the magnetic force and make the bar magnet fall even faster. Thank you for watching my presentation.